when a impact happens on the natural environment, for instance, an oil spill, if we don't understand what the baseline is, it's hard to tell after something happens what a return to normal means. And so it's a very difficult thing to do unless you monitor before something happens, while it happens, hopefully, and then after it happens. And so this project is an effort to better understand the life cycle, if you would, of that event. So the easiest way to do that, most cost-effective way, comprehensive way, potentially, is by using robotics to start creating a baseline. And that baseline, whether it's chemical information, in this case it was chemical information, doing chemical mapping, along with looking at the seafloor to understand its structure, to be able to do that before any work is being done. In this case, one of the waterways will be dredged. That approach can be highly benefited from using automation technology and robotics. The three major targets of this project were, we wanted to show we can have autonomous control on the platform in a couple different scenarios. Two is applying sensors on there that can both create chemical maps along with the seafloor mapping. And then the third is ultimately to fuse all that together to create a kind of unified picture of what that waterway looks like. So one of the things that's interesting about applying robotic technologies is that it allows us to start thinking and moving the laboratory out into the environment and being able to keep that out in the environment. In the particular deployment day, it was low temperatures in the 40s, very windy, and humans, after just a short spell, wanted to try to get in out of the weather. The robots don't care. They stay on the water, they continue to make the measurements, and that's one of the main advantages that having robots do. They can start to do things in conditions that humans generally start to avoid. So we chose to take two particular waterways that were within the city environment. One was residential, surrounded by homeowners, and the other one was a more industrial waterway that had greater traffic on it, plus industry surrounding it. Our interest was to be able to go and start doing systematic mapping to build a picture of what the seafloor looks like, and then also build a picture of what the chemical composition distribution was between the two waterways. We had a group of scientists also we're collaborating with. Tim Short and Strawn Toller for SRI provided the chemical sensor, the mass spectrometer. Brian Gregson was providing technical support to the mass spectrometer. We also had Frank Johnson, who was from CSA, and CSA had the mobile platform. Sean Hickey provided the 24-foot Parker center console boat, which was instrumental because it allowed us not only to observe the ship in certain circumstances, but allowed an additional county scientist to take sound velocity measurements to compensate and adjust the measurements that the machines are doing. Several things we learned from this: how to increase our ability to deploy efficiently. So that's always a very critical task. Two, we learned some variations on the chemistry at first analysis of the data. We learned we need to integrate obstacle avoidance, which is something we've done in the past at IHMC, and it's an area we can contribute to the robotics community. So we have future plans, a continual evolution of this platform with greater sensor capability, with the ability to adapt on the water for safety, and also to be able to then interact with sensor technology that's underwater. So we get a much more comprehensive map making, both with the mobile vehicle connecting the dots, if you would, between the underwater moored sensors. The holy grail is to create an intelligent waterway, measuring the changes that are occurring in the waterway, and that would then be of interest to people responsible for the waterway, and then also for the general public to better understand the health of the waterway.